This video will be on periodicity. We'll primarily be going through periodic table trends, so we'll start by looking at the periodic table, the trends for atomic radii, core charge, state at room temperature, melting point, electronegativity, ionization energy, metallic character, and reactivity. These are our relevant syllabus dot points. We should all be familiar with the periodic table by now. It's a table which labels where all of our elements are. The periods are going to be the rows on the table, and the rows are going to indicate an increasing number of protons as we move from the left-hand side to the right-hand side of the table. The groups, however, are the columns of the tables. So if I say this is group 1, that will be group 2, 3, 4, all the way up to group 18. As we go down the groups, what is happening is we're actually indicating an increase in the number of electron shells. Atomic radii refer to the radius or the size of an atom. So as we move from the left to right across the period, we're going to be increasing the number of protons and electrons which exist in the atom. This means that there is going to be a greater electron to proton attraction occurring between the outer electrons and the nucleus. Now, if the outer electrons are moving towards the nucleus where the protons are, then what's going to happen is we are going to compact the size of the atom and the atomic radius is going to decrease. As we move from the top of the group down, what is happening is we are going to be increasing the number of electron shells. What's going to happen or result from this may seem counterintuitive because we're increasing the number of electrons. So it would make sense that the electrostatic attraction would increase to make it smaller. But actually this is not what occurs. We're introducing another shell and something called the electron shielding effect is going to occur. What really happens is the inner electrons are going to absorb the electrostatic attraction from the inside and repel the outer valence electrons. This is going to cause an increase in the atomic radius. So the core charge is the charge which is experienced by valence electrons. We can calculate the core charge simply by subtracting the total number of electrons by the inner number of electrons. So for example, with this example neon here, neon has a total of 10 electrons, 8 of which are valence electrons and 2 of which are inner shell electrons. This means to work out the charge, we can take the total 10 and subtract the inside 2 in order to give us a charge of plus 8. Now on the periodic table, S and D block elements are generally going to be solid, except for hydrogen and helium in the S block. There's a loose trend of elements that are getting less solid as we move from the left-hand side of the periodic table to the right-hand side. However, it's important to note that there's no definite trend. Note that group 17 and 18 is mostly comprised of gases at room temperature. So the melting point is the temperature at which a solid turns into a liquid. The stronger the bonding, the higher the melting point, and we'll talk more about bonding in the bonding section. Again, there's no particular trend in the melting point of substances. Generally, elements which are solids at room temperature will have a high melting point. Electronegativity is an important concept which will help aid your understanding of bonding. Electronegativity is the tendency for an atom to gain a valence electron. We might ask ourselves, why does an atom want to gain a valence electron? Well, let us remember the octet rule. Atoms want to have a full 8 valence electron filled valence shell. This is primarily why we see electronegativity increase from left to right across the period. So something like a group 17 element, chlorine, has 7 electrons in its valence shell. It only needs one more valence electron in order for it to complete the octet, and so it becomes more desperate to want to complete it than something, say, in group 16, which has 6 valence electrons. If we go down the group, the electronegativity is going to decrease. And the reason for this is because there is less nuclear attraction between the outer electrons and the nucleus. The D and the F block elements are going to be exempt from this electronegativity rule. Here's a periodic table with the electronegativity values of various different substances. Notice that it's going to increase as we go from the left to the right, and it decreases as we go top down. Most group 18 elements have zero electronegativity because they have a fully filled valence shell. So ionization energy is somewhat the opposite of electronegativity. When a substance becomes ionized, it means that it's had one of its valence electrons removed. The ionization energy is the minimum amount of energy that's required to remove a valence electron. Ionization energy is going to be the lowest for group 1 substances, and this comes down again to the octet rule. Substances want to have a fully filled valence shell. Group 1 substances have only one electron in their valence shell, so if they could have that one electron removed, then they would be able to have a fully filled valence electron shell. This means that for something like a group 1 element, it is going to require much less energy to ionize them than something say group 4 or group 5. Thus, the ionization energy is going to increase from the left-hand side to the right-hand side across the table because it's getting more difficult to ionize elements with more valence electrons. Down the group, however, it's going to become easier to ionize. And the reason for that is because the increase in the number of electron shells means that valence electrons are going to be more loosely bound, and thus the ionization energy of the group decreases. Here's a diagram which demonstrates the ionization energy required for various elements. Notice that the lowest values are going to generally consist of group 1 elements like sodium, potassium, rubidium, or even cesium. The metallic character of a substance can be quantified by considering how easily ionizable it is, how shiny it is, lustrous, electrically conductive, thermally conductive, and other reasons. Again, the reason why it's more metallic as we move from right to left across the period is because the valence electron is going to become looser and looser, meaning that it's going to be easier to ionize. Now, the reactivity of an element is multifactorial. However, in general, metals which are more ionizable are going to be more reactive. This is because, if we remember, metals tend to react by removing the valence electrons. Non-metals, however, are going to react by gaining electrons, and this means that the more electronegative non-metals are going to be more reactive. The reactivity of multiple reactants with water is given on the table. Group 1 and 2 metals in period 3 or higher will react with cold water to produce metal hydroxide and hydrogen gas. Non-metals, except for the group 7 halogens, will not react with cold water. Halogens, however, will react with water to create hydrohalic or hyperhalous acids, and we'll learn about the nomenclature for these compounds in Module 6. Fluorine reacts with water to produce hydrogen fluoride and molecular oxygen.